Okay, this is Module 4, and this is the lessons 2 through 11, numbers 20 through 24. I thought I had these on there, but apparently I didn't, so here they are. It says, on his way to work every day, Frank passes through 2 intersections with traffic signals. Sometimes the lights are green when he arrives at the light. Sometimes they are red, and he must stop. The probability that he must stop at the first signal is P first is equal to 40% or 0.4. The probability that he must stop at the second signal is P second is equal to 0.5 or 50%. The probability that he must stop at both lights is 0.3. Suppose we randomly select one morning that he travels to work, and we look at the outcomes of the 2 lights. A, describe the event first, not second, in words. So that would mean that he stops at the first light, but not at the second light. Okay? Now it says list all the outcomes in the sample space. Okay. So basically what is all the possible combinations of stopping or not stopping at the lights. So, and remember, if we just say first, that means he's stopping at the first. So we would say stopping at the first, but not, let's just say, not the second. Okay? That would be what we set up here. The other one is not stopping at the first, but stopping at the second. Then we could have stopping at both, so the first and the second. And then we could have not stopping at the first and not stopping at the second. Yeah, and that's it. Okay? Calculate P for the first or the second, and interpret your result in the context. Okay? So, the probability that they will stop at the first was 0.4, and the probability they'll stop at the second is 0.5. So we can add that together, 0.4 plus 0.5. Then we're going to subtract the 0.3, the odds of them stopping at both. Okay? And so that would be, what, 0.9 minus 0.3 is 0.6. So 60% chance that they would stop at either the first or the second. So stopping at least one is how we would say that. Okay? Now it says calculate the probability of the event described in Part A. Part A was the first, but not the second. So to do that, I think what I would want to do is draw a Venn diagram. I think that'd be the best thing to do, or the easiest thing for me to do. I guess you could do not a frequency table, a table, maybe like I wouldn't do a 1,000, but maybe a 100 table. But I'm just going to do a Venn diagram. So here, and this is the first, this is the second, and we would say the odds of stopping at the first was 0.4. Stopping at the second is 0.5, but we also have to subtract the 0.3, which is going to go here. So that would be 0.1. And this would be, if we subtract the 0.3 here, it's going to be 0.2. Okay. Now, this is a total of 0.06, so this would be 0.4, where they get to go straight through. Don't stop it either. Okay, so what did the question ask? Calculate the probability in A. A said stopping at the first and not the second. So that would be right here. So that would be 0.1. Now E says, are the events stopping at first light and stopping at second light independent? Well, no, we know that real easily because it says 0.3 is equal to 0.4. Well, that's not true. Oh, wait, hold up a second. Stopping at first light and stopping at second light independent. That's not right. That would be, we would have to, we'd have to times that by 0.05. And it's still not the same. So, yeah. So no, they're not independent. Okay. This is the first, right here, this is the first and second. And this would be the first times the second. And those are not the same. Okay? Now, ELF says, assuming the probability of stopping at the first signal does not change from day to day, how surprising would it be for Frank to have to stop at the first light 5 days in a row? If he does have to stop at the first light 5 days in a row, would you question the model that assigns a probability of 50% to the first light each day? Okay, so since it's stopping at the light, the first light, 5 days in a row, and the first light is 0.4, we would just multiply that together 5 times. And if we do that, that equals about 0.0102. So that's only about 1%. Okay, so this is a very small possibility, and it would be very surprising. Okay, you need to know all of that for your test, I'm sure. All right, now 21 says an online bookstore sells both print books and ebooks. And customers can pay with either a gift card or a credit card. Suppose that the probability of the event print book is purchased is 0.6, and that the probability of the event customer paying a gift card is 0.2. If these two events are independent, what will the probability that the randomly selected book purchase is print book paid for using a gift card? Well, all we would have to do is simply multiply those two together. And that would just be 0.12. And that would be the probability. So if it says that the events are independent, remember, we can just multiply them together. Now, B says, suppose that the probability of the event ebook is purchased is 0.4, and the probability of the event customer pay using a gift card is 0.2, and the probability of the event ebook is purchased with a customer pays using a gift card is 0.1, are the two events ebook is purchased and customer pays with a gift card independent? Explain why or why not. Okay, so they would, we would multiply, let's see here, it is purchased, so that's 0.4. We get that right here. Customer pays using a gift card is 0.2. So we would multiply that together. And that would give us 0.08. Okay, so the probability of the event is purchased with a card and customer pays with a card is 0.1. So that's not the same. That is not equal to 0.01. So we would say that these are not independent. Okay, page 3. Number 22 says, airlines post the estimated arrival times for all their flights. However, sometimes the flights arrive later than expected. The following data report the number of flights that were on time or late for two different airlines in November 2012 for all flights to Houston, Chicago, and LA. Use the data to estimate the probability that a randomly selected flight arriving in Houston will be on time. Okay, so what we have to do is we're going to have to take the sum of them arriving on time, which would be 7,000. I'm going to write it up here, 7,916. And then we would need to take the sum of all of this. And that would be the easiest thing to do is to say 1,087. So we would now add that together, plus 1,087. But we're going to have 7,916 over, what is this? 3, 9,003. And the answer would be we have 89%. Okay, so you got about an 89% probability that you will arrive on time when flying to Houston using either of those airlines. Now, consider only flying to Chicago and Los Angeles for these two airlines combined. Explain what it means to say that the events arriving on time and Chicago are independent. So, to say that they are independent would say that the probability of arriving on time is the same for Chicago as it is for Los Angeles. It would not matter whether you're flying into Chicago or you're flying into Los Angeles. Both of those are going to be the same. Okay? So the likelihood of arriving on time does not matter whether you're flying to Chicago or flying to Los Angeles. Okay? So we're just going to say it doesn't matter where you're flying. That's what that would mean. Okay? Now, C says, do the events arriving on time and Chicago appear to be approximately independent, and explain your answer. Well, if you're on time in Chicago, that's going to be 8,796 over, well, we got to do this little calculation here, over 10,686. And that is going to be about 82%. So that's Chicago. Now to do for Los Angeles on time, you would say 3,251 over 2,693, 3,962, and that's going to be about 82% as well. So since they are the same, that means that they are independent. We would say that they are roughly independent. Page 4. 23 says, the average height of 140 million U.S. males is 5 foot 10 inches. Some males from the U.S. become professional basketball players, not the ones that are 5 foot 10 inches. I promise you. The average height of the 350 to 450 professional basketball players is in the NBA is about 6'7". There you go. Which of the following probabilities should be larger, or would they be similar? The probability that a U.S. male over 6 foot tall is a professional basketball player. Well, I am 6 foot tall, and I'm nowhere close to being a professional basketball player. But we could say that the probability that the U.S. male over 6 foot tall is, so that would be like saying tall and they are NBA. Okay. So it's fairly high to say that the NBA players are tall, yes. Okay. What about the probability that if you're an NBA player, so if you are an NBA player, then you are tall. Yeah, that's much more likely to be the probability. This would be much higher. That if you're in the NBA, you are tall. It's not really probable that just because you're tall, you're in the NBA. So this probability would be higher. Okay. Now, 24 says, a researcher gathers data on how long teenagers spend on individual cell phone calls in number of minutes. Suppose the research determines that these calls have a mean of 10 minutes and a standard deviation of 7 minutes. Whoa, okay. Suppose the researcher also claims that the distribution of the call lengths follows a normal distribution. Sketch the graph. Displaying the distribution, be sure to add a scale and to label your horizontal line. Okay, so that's easy. We would have this would be our minutes. This would be 10 as our mean. And over here, it would be about 3 minutes. Over here, about 17 minutes. And that should be about it. I'm going to probably put it like that because you're not going to have anything. So 2 standard deviations away would be like a -4, where you're not going to have a -4 phone call. That's just not possible. Okay.